Okay, so let's start. Maybe in the meantime, you already had some look onto the organizational information. So just for your knowledge, all of you participants are muted. So if you have any questions, comment, or something else, just use the chat or this question answer tool. Um, so as soon as you have a question, just type it into the chat, but I will answer all of your questions then at the end of the webinar. So there will be a moderated question answer session. Maybe if I see the question, I can uh, put that already into the flow of the webinar. So just type that into the chat and I will answer that for sure during this webinar. So also in case of problems, just use the chat. So I hope you see my screen with the presentation. So, and I hope everyone can hear me well. So, furthermore, for your knowledge, the webinar will be recorded. After the webinar, probably tomorrow, you will get an email with the link to the recording and some further information about the webinar. And additionally, we are very happy to receive some feedback after the webinar if you like the presentation, the topic, or if you have some tips or or just some ideas what we can offer as well in our webinar series. So we are very happy to receive some webinar. Just write us an email about that. So let's start with the topic of today, the Hall effect analyzer. So in this webinar, I will prepare the Linsize Hall characterization system. Shortly, we denote it with HCS. So for what the system can be used and which possibilities it offers. Today's agenda will be, first, I will give a short introduction into myself and the company and in the topic itself. Then you will get an overview about the different models of the Hall characterization system. Then I will show which possibilities and add-ons the system offers. We will have then a short look into the software, what can be realized there. And in the end, I will give some examples for some measurements. And to close that, I will answer then all of your questions. So for those who did not participate in any of our webinars up to now, first of all, my name is Erika Hahn. I studied physics and I'm working for Linsize since 2020, so for 3 years right now, and I'm responsible for the application laboratory for the topics of thermal conductivity and thermoelectrics. Our company, Linsize Messgeräte, was founded in 1956 by Dr. Maximilian Linsize in Selb, which is in northern Bavaria. So this is Dr. Maximilian Linsize. After him, his son, Klaus Linsize, owned the company, and now also his two sons, Florian Linsize and Dr. Vincent Linsize, are leading the company. Our main business area is the manufacturing of measurement instruments for thermal analysis, thermal conductivity, and thermoelectrics. But we also offer a service lab. One of this you can see here, here in Selb. Most of the work is done here in Selb, but we also have some sales and service locations in the US, China, and India. And we also have more than 65 distributors worldwide, so that in almost every country there is a contact person. In general, the company started with such data loggers, but with the invention of computers, this was not necessary anymore, so the company focused more into thermal analysis. On the next slide, you see our general product range. So it ranges from classical thermoanalysis like DSCs or thermobalances and STAs to dilatometers, thermomechanical analysis, as well as thermoconductivity, thermodiffusivity, where we offer a broad product setup, and thermoelectric analyzers, as well as Hall effect measurements. And we offer also instruments for thin film analysis in respect of thermoconductivity as well as thermoelectric properties. What makes Linzers very unique is that we offer a high level of customization. So we have a lot of different options with which the system can be equipped. And additionally, if you have or if the customer has a very special task and wants to combine maybe different instruments or there are some special requirements, we are typically very open for that and try to find the best suiting solution. So let's introduce shortly the Hall characterization system and then have a closer look onto that. So with our Hall characterization systems, Hall effect measurements can be performed, and with that, the determination of the Hall coefficient, the Hall mobility, charge carrier concentration, the electrical resistivity and conductivity, as well as the type of the charge carrier and the sheet resistance, the magnetoresistance, and also the Seebeck coefficient with an adapter can be determined. So with just one measurement, a lot of different properties can be calculated or determined. So there's a lot of properties determined just with one instrument. So the HCS allows the analysis of thin films to bulk materials and uses for that the Van der Pau measurement method, so a 4-point probe measurement method. The main options which can be added are a gated Hall bar measurement method as well as an illumination option. Before we go on, maybe we have a short look into theory. What is the Hall effect? And on the next slide, I will show the Van der Pau measurement method. So the Hall effect appears when a magnetic field is applied perpendicular to a current flowing conductor. So the current direction is indicated in this example or in the sketch here, and perpendicular to that, a magnetic field is applied. Due to the Lorentz force, a voltage is generated due to this magnetic field applied to the sample, and this voltage is created perpendicular to both the direction of the current flow and the magnetic field. This generated voltage is called the Hall voltage and can be calculated like that. So you need to know the strength of the current flowing through the conductor, the strength of the magnetic field. You need to know the sample thickness, and specific for a material, there is a Hall constant which needs to be used here for the Hall voltage calculation. So if you have then the Hall voltage and the rest of the parameters, you can determine then this Hall constant or Hall coefficient. So the sign of the Hall voltage also gives direct information about the type of charge carrier. So if it has a minus sign, the dominant charge carrier are electrons. If it has a plus sign, the charge carriers are mainly holes. Also, with the Hall effect measurement, one can easily determine then the charge carrier concentration using here this Hall coefficient. Also, what can be directly determined with this measurement or the Hall coefficient is the Hall mobility. For that, you also need to know then the electrical resistivity, which can be determined with the with this Van der Pau measurement method as well. In general, the Van der Pau method describes a 4-point measurement method for determining the sheet resistance and the Hall coefficient. Advantages of this method is that almost every sample shape can be measured. So if the sample is a round, rectangular, square, or clover leaf, or something irregular shaped, like indicated here in the sketch, everything can be measured. But there are two main requirements to the sample. So on the one hand, the sample thickness must be homogeneous and small in relation to the distance between the contacts. The 4 contacts, ideally point contacts, must be additionally on the very edge of the sample, and the contact area must be small in relation to the area of the sample. So these are the main requirements so that this Van der Pau measurement method works. The measurement principle itself is described here. So you apply a current between two contacts at one edge, so for example A and B, and measure then the voltage drop at the remaining contacts on the other edge, so C and D, like indicated here. And this is then repeated in vertical and horizontal direction. For the evaluation, one uses then here this Van der Pau equation. You see here that the resistivity can be calculated from here. You use also the sample thickness D for the calculation. And also the measurement of the resistance. Here R, A, B, C, D means that the resistance is calculated from a measurement where a current is applied between contacts A and B, and the voltage is measured between C and D. Same here for the second term, which means that a current is applied between B and C, and the voltage is measured between D and A. So the repetition in vertical and horizontal direction. For the determination of the Hall constant, one uses then this formula. So also the sample thickness is relevant, as well as the magnetic field strength, and also this difference in resistance, where on the one hand, no magnetic field is applied, and then a magnetic field is applied onto the sample to get here the difference. So now we know how the measurement methods and what the property itself means. And now we can have a closer look onto the systems. So Linsize offers 3 categories of the Hall characterization system, the HCS 1, 10, and 100. Most of the applications, or almost every application, can be realized with those 2 instruments. So the basic instrument, the HCS1, uses a permanent magnet, which has a maximum magnetic field strength of about 0.7 Tesla, and the magnet can be moved automatically with a motor, and the temperature range which can be covered is from liquid nitrogen to 600 degrees. Same temperature range can be also realized in the HCS10, but here we use an electromagnet with a magnetic field strength of about 1 Tesla, and what can be used here as well is an AC magnetic field option, so that an frequency modulated magnetic field can be used. So the HCS1 covers most of the applications. For a bit more challenging applications, as well as materials with a low mobility, the HCS10 can be used. And for very demanding and for very special applications, the HCS 100 can be of interest, but this system is only available on request. And this system uses then a Hallbach array, which can generate a magnetic field of about 0.5 Tesla, either in DC or AC mode. and has a lower temperature range, which can be covered from room temperature to 500 degrees Celsius. On the next slide, you can see the main specs. So resistivity, carrier concentration, and the mobility. You see directly from HCS1 to 10, a magnitude more in respect of mobility can be realized just due to the possibility of this AC magnetic field. And the HCS 100 has a bit more power, but as mentioned before, this is really instrument for very special applications and typically is not of interest as mostly the HCS 1 and 10 can be used. But I just want to mention that, and in the following I will focus more on these two types of instruments. Now we have a closer look into the instrument, how these are set up. So starting with the HCS1, the device, here you see a cut through the system, how it is set up. So in the middle, first of all, you have here the measurement sample, the measurement chamber, where the sample board, which you will see in a later slide, will be inserted. Here in the measurement chamber, it is also possible to use a vacuum-tight chamber so that different atmospheres can be generated. And there are also then liquid nitrogen parts for either quench cooling system, where we can go down to minus 196 degrees Celsius. With a controlled cooling, we can go down to minus 150 degrees Celsius. Inside the instrument, there's of course then the permanent magnet located. In the middle, there will be a zero magnetic field, and on the one side, then the positive, and on the other side, then the negative field. Typically, this magnet is moved automatically with a motor, but in a more basic version, there are two handles so that the magnet can be moved manually. So you also see here then a cut through the other side. So you see here a little bit more this measurement chamber with the sample holder stage inserted. And here also there will be then the gas in and outlets. And we also have then the measurement electronics, of course, built inside. So now to the HCS 10, the more powerful device. Here you see again a cut through the system, but more simplified. So we also have here the measurement chamber, which can be also vacuum tight for controlled atmospheres. And we also have the liquid nitrogen in and outlets for either the quench cooling or the controlled cooling option. Inside the system, we also have for, of course, then the electromag or a magnet option here, the electromagnet, which allows either a DC power supply where about 1 Tesla can be applied, or one can use an AC power supply with about 1.4 Tesla difference in magnetic field. And additionally to the AC mode, a lock-in amplifier is needed so that more challenging samples, for example, low mobility samples, can be measured. The HCS system allows also the use of the sample holder fixture with the plug and play sample holder boards. And you can also use the CBIC option as well as the illumination option and the gated hall bar option. In comparison to the HCS1, the HCS10 allows, on the one hand, the use of the controlled magnetic field. So with the permanent magnet, you have only zero field, plus and minus magnetic field with a certain magnetic field strength. The electromagnet allows you then to really measure more different magnetic fields and have individualized magnetic field steps. With the AC power supply, the magnetic field will be not linearly then applied or linearly changed, but you will have here a modulated magnetic field. The advantage about that I will explain in a few slides later. So as mentioned in the beginning, or just in the last slide, we have different sample holder boards for different geometries. So for example, square, rectangular, round, or cloverleaf samples can be measured. Also thin films can be measured either freestanding or on a substrate. And we have sample boards for measurements up to 200 degrees Celsius for smaller samples and for quite large samples. So here you see a sketch or a picture of various sample holder boards. Each of these are set up in the same way. So we have here the sample board with the connector, which will be inserted into this adapter. And with this adapter, you can insert that then into this measurement chamber. On the front, you have the position for the sample with some indications on different sample sizes which are possible. And there are spring-loaded contacts, which contact then the sample on the four edges of it so that the van der Pau measurement conditions or requirements are fulfilled. What is very unique here is that we have an integrated heater here on this measurement board so that the sample will be heated from the bottom, and by that really fast heating and cooling rates can be obtained, as not the complete measurement chamber needs to be heated with an external furnace. Only then the cooling will be performed then with the liquid nitrogen and not with the measurement board. In a more special setup, we use then ceramic measurement boards so that measurements up to 600 degrees Celsius can be realized. But for the usage of this kind of sample holder, so the ceramic version, also the measurement electronics, so the hardware needs to be changed a little bit. A very nice feature here is that the system is a plug-and-play system, so you can use several measurement boards and just plug in one after the other into this adapter. So if one wants to have a high throughput of samples, one just uses different sample boards. So there is also a special measurement board, the Seebeck option. So this measurement board allows you then the measurement of the Seebeck coefficient, and it looks like that. We have here the possibility to measure from liquid nitrogen temperature up to 200 degrees Celsius. And for contacting the sample, we use thermocouples of type K. And here on the right, you see the sketch of how the measurement principle works. So we have here the sample, and we have several thermocouple wires which touch the sample orthogonally to the direction of the temperature gradient. And both contact spots should share then the same temperature, but this is realized by that the sample thermocouples are really close to each other. We use here an aluminum thermocouple wire as well as a chromo thermocouple wire. Ideally, the sample is bar-shaped so that it really fits here into these contact pads, and the complete measurement will be automatic in respect of the operation itself and the evaluation. So on the next slide, you see then a sample inserted the board here. So you see the contacts of the thermocouple wires and the rectangular bar-shaped sample. So the temperature of the cold side and the temperature of the hot side are calculated using the thermal voltage of the thermocouples, and the absolute temperature measurement is performed by a PT 3000. The thermocouples wires forming one thermocouple are very close to each other and therefore minimize the temperature measurement errors due to temperature non-uniformity of the two contact spots. The Seebeck voltage is then measured between both negative thermocouple wires so that the Seebeck voltage occurs in the exact same spots where the temperature is measured. The Seebeck voltage is recorded along with the temperature gradient, while the gradient heater, which is, by the way, located in the back side of the sample holder, so the gradient heater power is linearly increased, and in the end we will get a curve like that. So you see here the thermal voltage as well as the sweep of the temperature difference. The duration of such measurement sweep is typically about 30 to 90 seconds, so it's a very fast measurement. The slope here can be used then to measure or determine the Seebeck voltage over temperature, and we find out in the end then the Seebeck coefficient in respect of the temperature using here the slope method. Also, since the measurement is so fast, the offset drifts have very low impact onto the result. A further option with which the instrument can be equipped is the illumination option. So it is an optional add-on so that illumination on the sample can be simulated, and by that then the Hall effect in respect of this illumination can be tested. We have three available possibilities, so blue, green, and red light. So if the behavior of the sample under specific illumination should be analyzed, we have here this illumination option available. As mentioned before, this HCS10 offers the possibility of using a DC and AC magnetic field, whereas the HCS1 system only have the possibility of a DC magnetic field. The AC magnetic field measurement method offers some more possibilities, especially in regard of low mobility materials. So the reason behind that is, in general, when there's no magnetic field, the Hall voltage should be 0. But in reality, an offset voltage can be measured, which contains a contribution of a misalignment voltage, shortly with MA, and the thermoelectric voltage, shortly TA, can be detected. So the misalignment voltage appears just due to symmetry reasons. So your sample is not perfectly symmetrical, and in the Van der Pol measurement method, for example, it is required that the point contacts, as small as possible, are at the very edge of the material, but in reality, this cannot be realized 100%. So you typically have a contribution of this misalignment, and the thermoelectric voltage can be detected just as two different materials get in contact by just contacting the sample itself. So in DC magnetic fields, typically by just inverting the current and the magnetic field direction, you can remove those two contributions. But for materials which have a very low mobility, so below about 1 centimeter squared per volt second, it might happen that the signal of the Hall voltage is much lower, so significantly lower than the sum of the misalignment voltage and the thermoelectric voltage. So by the inversion of the current and the magnetic field direction, and by subtracting that from the measured signal, only a very, very low value will remain. And this is very hard to resolute in a good agreement with accuracy, so that in this case, the DC method will just come to its limits. The solution is to use a frequency modulated or a modulated magnetic field, so that a sinus term will be added here as well to the Hall voltage. As the Hall voltage, if you remember, is directly dependent on the magnetic field. So if you have a sinus curve onto the magnetic field, this will be also here on this Hall voltage. The advantage here of using this AC magnetic field is that these offset voltages, the misalignment voltage and the thermoelectric voltage, do not depend on the magnetic field. So by having the sinus on the magnetic field, you will not have the sinus on both of those two contributions. And by that, these still remain as a DC signal and thus can be more easily be separated just by using a lock-in amplifier. With the lock-in amplifier, you can then separate the AC signal, which belongs here to this Hall voltage, from the undesired DC signal of this offset voltages. So in samples with a low mobility, the usage of the AC magnetic field can be advantageous, and in our case, this can be realized then with the Hall characterization system 10. In each of our Hall systems, we have an advanced measurement electronics, which allows optimized DC measurements and has different decades of input current to really cover a lot of different materials. The AC measurement is an upgrade where we use also a lock-in amplifier. So we have here also different frequency ranges possible and different current ranges as well. The integrated electronics allows also different sequence control like heating, cooling, gas doses, and also the polarity changes, so that our measurement electronics allows a lot of different measurement modes in an optimized way. So now we have a look onto the software so that you get an indication of which possibilities our software, our system offers. So here you see a screenshot of the first part of the system, so the settings. First of all, on the file and controller, you have the possibility to change a little bit the system settings and the stabilization criteria, for example. You see here also the current system status. So what is the temperature, what is the target temperature, and what power in heating or cooling is used to achieve this target temperature. Of course, you have the possibility to give a sample name, and for the evaluation, the sample thickness is needed, which also needs to be typed in. Advantages is here this button, find maximum current. By that, different current ranges are tested to find out what is the maximum possible current which can be used without damaging the sample. Then you can insert a measurement current and also select if only resistance, if only Hall, or both of properties should be determined. Then in the measurement settings, you set up your heating profile or your temperature profile. You can either measure only at room temperature or program a temperature-dependent measurement either manually or using a profile wizard. You can also control here, for example, the heating or the cooling rate. For a good measurement, one needs an ohmic contact between the spring-loaded pins and the sample. And for that, there is a connection test as a second step. You see it here. Here's the connection test. With this tool, you can set up a current range um, with the lower and the upper limits and the number of steps in between, so that the system will linearly increase then the current and measures the voltage, so that you will get a UI curve as indicated here. And in case of an ohmic contact, you see a linear behavior. Additionally, the resistance is calculated in dependence on current, and in the ideal case, the resistance does not change that much. So this is also an indication of the quality of the contact. So if those curves do not show the ideal behavior, one can try to prepare the contacts or modify them a little bit. For example, you can sputter some gold edges onto the sample or a solder contacts, or use, for example, a silver paste just to have maybe an improved contact. After that, you can try again this connection test until you have an ohmic contact between the pins and the sample itself. During the measurement, you will see then this window where all the parameters are summarized, so the current sample temperature as well as the current which was used for the measurement. You see here the Hall voltage in dependence on the magnetic flux density, so without magnetic field plus and minus magnetic field, also with the reversal of the current flow. You see all the raw data regarding the voltages and the Hall voltages. And on the bottom, you will see then the calculated result of sheet resistance, mobility, resistivity, conductivity, the charge carrier concentration, and the Hall coefficient, as well as the magnetoresistance. If you perform the measurement in dependence on temperature, this will be shown here as well during the measurement. So you see here the Hall coefficient as well as the resistance in dependence on the temperature. So that directly during the measurement, the plot here will be generated, which can be stored and exported as well. So coming now to an end, I want to just quickly show a few measurement examples which we already performed with our system. So typically the Hall characterization system is used in the semiconductor industry, where semiconducting materials, typically thin films, are measured. So this is the typical application which is realized with the Hall characterization, but of course different cases can be covered as well. On the left, you see a bismuth antimony thin film of about 150 nanometers, which was measured with an HDS-10 from room temperature to 180 degree. So you can clearly see here the decreasing resistivity, mobility, and Hall coefficient. On the right side, you see indium tin oxide, shortly E2. The thin film here was about 185 nanometer, and the sample was prepared by a sputter deposition, and the measurement was performed from about room temperature to 150 degrees Celsius. There's a typo in there. And this E2 sample is also used for in-house reference. So this is the kind of material with which we test the performance of the instrument to validate that the system is measuring correctly. And the last example is a Seebeck coefficient measurement, where a constant Hahn reference sample was measured from about minus 130 degrees Celsius up to 180 degrees Celsius. And for each temperature step, which you can see here, the Seebeck coefficient was determined using the slope technique we have seen before. So you see here the temperature gradient sweep where the thermal voltage is measured, and using here this linear relation, the Seebeck coefficient was measured. So this was all from my side. I want to thank you for your attention, and I hope you got an indication of what our whole characterization system does, what possibilities it offers, and which add-ons are possible.